Hi, welcome to week 9 of this course. So, we are at the last week of this course. We started with the 8-week plan and we extended that to 9 weeks to accommodate a few additional topics that were requested by several students. So, in this week we will look at number representation and we will look at arithmetic circuits. So, we have touched upon some of these things in several other weeks so far, but in this week we will consolidate all of the things that we have seen so far. In fact, we have done some programming assignments already based on some of the knowledge that you have. In this video and in the week that's in this week we will take all of these concepts and formalize all of the ideas. So, we will start with number representation. So, the first number representation that we started with in the beginning of the course is positional number system. So, positional number system is one in which the position of the digit dictates a weight and we added weights appropriately that gave us the value. So, in all the in this video what we will see is the notion of if you are given a bit vector, a sequence of bits, so you are given a collection of bits, we will see how to interpret them properly. In a positional number system, if I give you a n bit vector, then we treat each of these bits as though they indicate a weight, and we have a simple formula which will convert the weights to the appropriate value. So, for example, if I give you a base r and let us say di is the digit at position I, this could be in any base, and let us say the base is r, then and let us say there are numbers of this form. There is some n digit number before a decimal dot and there is an m digit number after the decimal dot. So, this could be these digits could be decimals, these could be hexadecimals, binary, octal, it does not matter. Whatever it is, if you are given a number of this form where it is n digits followed by m digits, then the value that we attach to it or the interpretation that we have for this one is for I equals minus m to n minus 1. So, minus m all the way up to n minus 1, we take di r power I. So, that is the digit at position I multiplied by the base to the raised I. So, this r power I is the weight that is assigned to the position. So, for example, we looked at this 12.34 base 10. So, this has 2 digits in the front and 2 digits after decimal. So, you start with this one, this is 4 into 10 power minus 2 plus 3 into 10 power minus 1 plus 2 into 10 power 0 plus 1 into 10 power 1, that is the equivalent value and that is the representation 12.34. So, if I give you some number like 111.101 base 2, then you would be able to interpret that by putting appropriate weights and so on. This is something that we already know. So, if you are given a vector, what happens is this sequence of digits that you see as a vector, if you want to interpret that as a value and if you think that it is a number, then we are interpreted by assigning appropriate weights and so on. So, the positional number system is something that we have done, it is straightforward, we have seen this before. So, we will start with the so called representation of signed numbers. So far we have not discussed how numbers both positive and negative are represented, and this is a routine thing that we deal with in computers. So, computers should be able to store and manipulate negative numbers also. It is not that all the operations that we have are positive in nature. For example, a bank balance could go negative. So, things like temperatures could go negative and so on. So, we want to be able to do arithmetic operations like addition, subtraction, comparison, multiplication and so on negative numbers also, which essentially means first of all we need a representation for the negative numbers. So, us as humans, we look at a sign which is minus in front of a number and we say, oh, this is a negative number, but we need a representation which will also accommodate what are called signed numbers. Signed numbers mean the numbers are, so the signed numbers represent both positive as well as negative numbers. So, basically if you go and look at the number series, right, there are infinitely many numbers both positive and negative, and however a computer typically has a fixed storage. So, for example, if you go and look at most computers that are available nowadays, you will either see that they are 32-bit computers or 64-bit computers. So a 32-bit computer is one in which the internal representation allows you to have only 32 bits, which means you can represent 2 power 32 distinct values. In this 2 power 32 distinct values, you have to accommodate both positive and negative integers. Similarly, if I go and look at a floating point value is typically also 32 bits, which means you can represent 2 power 32 distinct floating point numbers, right. So basically it is possible that you are given some storage, so let us say 32-bit number, and the number that you want to represent is much larger than that, which means this cannot be natively stored in your computer and manipulated on. As long as the number can be natively stored and manipulated, so there are circuits inside which will allow you to do that and you can exploit it. However, if a number goes outside the range of what can be natively represented in the computer, you need software techniques to deal with those. So what we will do first is we will look at 4 popular mechanisms by which we deal with signed numbers. So signed numbers are those in which we want to represent negative numbers or negative integers, to be more precise, 0 and positive integers. So the floating point representation is slightly outside the scope of this course. We will look at only signed numbers in the videos that follow. So there are 4 ways in which the signed numbers can be represented. They are signed magnitude representation, ones and twos complement representation, and XSB or biased representation. So let us start with the first one, signed magnitude representation. So in the signed magnitude representation, what we have is, if you are given an n-bit vector, we interpret the leftmost or the most significant bit as the sign and the rest as magnitude. So this gives us the name signed magnitude representation. So a n-bit vector will be interpreted as a 1 bit that is for sign and n minus 1 bits that is for magnitude. So the interpretation of this bit, the most significant bit, is if s is 0, then it is considered positive, and if s is 1, it is considered negative. And let us look at the range that this can represent. If I give you a n bit vector, then one of the bits is already lost to the sign, right, but then you have n minus 1 bits. For the n minus 1 bits, this n minus 1 bits can go from all the way from 0 to 2 power n minus 1. So with the sign magnitude representation, this s being 1 or 0 essentially doubles that range. We should be able to represent numbers from minus 2 power n minus 1 all the way to 2 power n minus 1, and since we have this restriction, so if I give you a 4-bit vector, right, unsigned representation, if I give you a 4-bit vector, you can only go from 0 to 15, you cannot go to 16. So that is why you have a strictly less than 2 power n minus 1 here, and x is strictly greater than minus 2 power n minus 1. So if you are given only 4 bits for signed magnitude representation, you will not be able to represent 8 and minus 8. You can represent all the way from minus 7 to 7. So the range is symmetric around 0. What that means is you have as many positive numbers as there are negative numbers, and 0 itself actually has 2 representations. So both 0 followed by all zeros and 1 followed by all zeros they both stand for 0. So this is actually positive 0 because you have sign as 0 and magnitude is 0, and this is negative 0, so sign as 1 and magnitude as 0. However, technically there is no difference between plus 0 and minus 0 for various arithmetic operations that we are going to do. So 0 gets to have 2 representations in this. So let us do a bunch of examples. So let us assume that we want to represent numbers using 4 bits. If you want to represent numbers using 4 bits, let us start with number 5. So number 5 is actually 101, the tightest representation is 101, but if I want to store this in a 4-bit representation, if I tell you that you have to store it using 4 bits, then the foremost bit has to be a 0. So let us take a look at this. 0 is interpreted as a positive number, so the rest of the digits signify a positive sum whatever integer is, and the rest of the numbers is 101, which stands for 5. So this is positive 5. Let us look at this number here, minus 5. So, for minus 5 you put a 1 followed by 5's binary representation, that is 101 itself. So, now what is the representation for 3? This is plus 3. So, plus 3 is, so 11 is actually the tightest binary representation for 3, and we are given 4 bits. So, the very first bit must be a 0 because it is plus 3. So, the first bit must be a 0, the most significant bit. Then the next most significant bit should also be a 0 because 3 has only 1, so it has only 2 bits. So, the representation for 3 should be 0011. Now, finally, think about what should this number be. So, it is 1 followed by 111. So, this means it is a negative number, and the magnitude 111 is for 7. So, this is for minus 7. So, I want you to go and do this as a little bit of an exercise. Convert the following sign magnitude representation into a 6-bit representation. So, assume that these are both sign magnitude numbers, but they are represented using 4 bits. I would like you to go and think about how to do this in 6 bits. So, I am going to give you the answer, but I want you to think about it. You may want to pause the video and then come back and look at the answers. So, let us look at this. 0101, 0101 is a positive number and the value is 5, and we want that to be represented in a 6-bit representation. So, in a 6-bit representation we should still start with the most significant bit to be 0 because it is positive, and 101 instead of 3 bits we will need 5 bits, the 5 bits will be 00101. So, that will be the 6-bit representation for 0101. Let us look at this number below, 1010. 1010 in a signed representation stands for negative 2, because 1 is for negative and 010 is 2. If you want this represented in 6 bits, then it should be 1 followed by 3 zeros followed by 1 0. So, clearly if you have a representation which is in fewer bits, if you expand it to more bits, you should always be able to represent it. So, that is how most of the sign magnitude, most of the signed representations work. If you have a representation, a signed representation of a number in n bits, you should be able to extend it to some m bits which are greater than n. It should always be possible. However, if you have a number represented with a larger number of bits, you may or may not be able to represent that using fewer bits. So, for example, if I give you number 9, writing 09 or 009 will extend the number of digits, right. So, I can write 9 as a 3-digit number 009, but if I give you a number 995, you cannot write that using 2 digits or 1 digit, you need at least 3 digits for it. So, the same thing applies in binary numbers also. So, what if you start with a sign magnitude representation of n digits, you can always extend it to some n dash digits greater than n. So, this is sign magnitude representation. So, to make this stick in your mind, I want you to look at this picture here. This is called a number circle. So, a number circle, this pretty much looks like a clock, only that there are a few differences with respect to a clock. So, in this case the number circle is representing 4-bit numbers. So, let us start from here and let us move around the circle in the clockwise direction. If you go in the clockwise direction, you see that it starts with 0000 and then goes to 0001, 0010, 0011 and so on, all the way up to 1111, right. So, these are all the 4-bit values that you can have. So, I am not talking about the interpretation of these numbers yet, it is just if I give you 4 bits, these are all the combinations that we have, and this is arranged in some increasing order of the values. So, clearly if it is unsigned interpretation that I attach to it, then this position will be 0, this position will be 1, this position will be 2, this will be 3 and so on all the way up to 15, right. So, a 4-bit unsigned value can go from 0 to 15. Clearly you cannot represent anything above 15, right, you cannot represent 16 and above. You can also not represent anything below 0, you cannot represent any negative numbers. So, this is the deal with unsigned numbers. Now, I am going to show you how to deal with signed numbers. So, I have the same number circle here, and in this number circle it is still going from 0, 0, 0, 0, 0, 0, 0, 1 and so on. The clockwise, it's looking like this odometer that I keep talking about, right? It's like the odometer running, which runs from 0000 all the way to 1111, and then it will roll back to 0000. So if you keep going in the clockwise direction, it is always like incrementing the meter, and if you go in the negative direction, it's like decrementing the meter. It's like the meter running backwards. But now if I want a signed representation interpretation for this, so the vector that is given is 0000, I want to see how to interpret it as a signed representation. So 0000 is, this indicates that 0 is so the first digit is a 0 and the rest are all the magnitude. So this 0 is for a positive number and you have 000. Similarly, all the way here, if you see, right, if you go from here all the way up till here, the first bit is a 0, which essentially means this half is all positive numbers and this side is negative numbers, all right. So let us see what these numbers are. So this is plus 0, this number would be plus 1, this vector will be interpreted as plus 2, this is plus 3, so on up to plus 7. If you start from here, this is minus 7 because it's this saying it's negative number followed by 3 bits which stands for 7. This is minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, and I already mentioned that we also have a negative 0 as well as a positive 0. So this is a positive 0 and this is a negative 0. So let me finish this. This is the signed representation or signed magnitude representation or interpretation of the numbers. And if you notice, there are a few things. So this is only for 4 digits. If I want to get the circular representation for 5 digits, you should draw a circle which has more values in it. So this has 16 values, you should be able to draw one with 32 of them, right? And again the 1/2. So if you draw a line from 0000 to, let us say, slightly to the left of 0000 to slightly to left of 0111 or the equivalent one, if you draw a line, everything to the right of that will be positive numbers, everything to the left of that will be negative numbers, and you will see that 0 and minus 0 are in the exact opposite corners. So this is the signed magnitude interpretation of these 4-bit values. So now let us go to the other interpretations. So if I go and look at what is called ones complement interpretation. So the ones complement interpretation is positive numbers are represented as is, there is no change in positive numbers. However, negative numbers are represented by performing bitwise complement of the integer. So let us look at this. If I want to get a 4-bit representation of the value plus 5, so the value plus 5 in binary is plus 0101, right. So if we can leave the plus sign, we can write it as 0101. However, if I want to represent minus 5 and if I want to represent minus 5 in ones complement form, then the way to do that is you take whatever is the n bit representation of the positive number, negate or flip all the bits, that is the ones complement representation. So if I take positive number and negative number, there will be flips of each other in ones complement representation. So all the positive numbers will have MSB equals to 0 and all the negative numbers will have MSB equal to 1. So according to this bullet point, both signed magnitude representation and ones complement representation have this similarity. If MSB is 0, then it is positive, all negative numbers have MSB equals 1. The range that you can represent is again very similar to the signed magnitude representation. So it can represent from minus 2 power n minus 1 all the way to 2 power n minus 1. So this is again very similar to signed magnitude representation. The range is again symmetric around 0, which means you have as many positive numbers as there are negative numbers that you can represent with n, and again as with signed magnitude representation, there are 2 representations for 0, namely 0000 which is for plus 0 and 1111. If I want to interpret that in as a decimal value, this 1111 in ones complement interpretation is I take the first bit the first bit tells me that it is a negative number. So, I will put this sign minus somewhere down, and 1 1 1 1 I will complement all of the bits, it will be 0 0 0 0. I will read the binary interpretation of that, 0 0 0 0 is 0, so it is negative 0. So, let us look at a few examples. So, we are going to assume that we want a 5-bit representation. So, we are going to go from 5-bit representation to decimal as well as go from decimal to 5-bit representation. So, let us see this number first, 0 followed by 1110. So, this one tells me that this 0 tells me that it is a positive number, 1110 is the magnitude in this case, right. So, the positive numbers are very similar to the sign magnitude form itself. So, this is 0 followed by 1110, which means it is positive. 1110 in binary is 14, so this is plus 14. Let us look at this number here, 10111. So, 10111 stands for a negative number because this is 1, and so if I take 10111 and I flip all the bits, it is 01000. So, 01000, if you interpret that as an unsigned binary number, it is 8. So, my answer to this question is minus 8. So, the first one is plus 14, the second one is minus 8. Now, let us look at how to represent 15, positive number 15. So, positive number 15 is 1111 in unsigned binary, and if I put a 0 in front of it, it is 01111, and that is actually okay for a 5-bit representation of this number 15 in 1's complement form. However, let us look at 16 and minus 16. So, 16 in binary in unsigned representation, it is a positive number, I should be able to represent that as unsigned number. Unsigned number would be 1 followed by 4 zeros, right. So, already 16 requires 5 bits. To represent 16, you need 5 bits even in the unsigned form. You will not be able to represent that in the 1's complement form, or even in the signed interpretation. You cannot represent 16 using only 5 bits in the signed interpretation as well as in the 1's complement interpretation. So, if you notice, I want 16, so 16 is already 2 power 4, right. So, 16 is 2 power 4, I can represent only from minus 2 power 3. So, let us look at this, I am sorry. So, we want a 5-bit representation. So, minus 2 power 5 minus 1 is minus 2 power 16, 2 power 4 less than x less than 2 power 4. What that means is x can take the values from minus 16 to plus 16, but the ends excluded. We cannot represent the ends, we cannot represent minus 16 and 16. So, it is essentially minus 15 to 15 can be represented, 16 and minus 16 cannot be. So, we cannot interpret this as, we cannot represent 16 using 5 bits. However, if you are asked to if you are asked to represent it using 6 bits, that is possible. For 16, you can represent that using 6 bits. So, let us look at some other conversions. In this case, we are taking a number which is smaller bits and we want to represent that in a larger representation. So, 01011, right. So, this is a positive number. By the way, 1011 stands for number 11, right. If you want to represent that in 1's complement form using 8 bits, then it is just take the 0 and append as many zeros as you want before that till, so in front of this till you get to this value here. So, this is 5 bits, if I append 3 zeros here in the front, then it is 000 followed by 01011, that is the representation for this one. Now, let us go and look at this number 10111. 10111, I know that it is a negative number because it is starting with a 1. So, what is the value for this? 10111 is, to find out the value, we note down the sign that it is negative, it is minus. 10111 is, if I flip all the bits, it is 01000, which is 8, right. So, this is the binary equivalent, or this is the 1's complement representation of negative 8, and if you want to convert it into a 8-bit representation from this 5-bit representation, all you have to do is add as many ones before this. So, let us take this one. So, 01011 appears as it is, we have added 3 zeros in the front, and similarly 10111 is as it is, we have added 3 ones at the front. So unlike the unsigned representation, remember these ones do not actually hold any weight, right? That is the key difference. If I tell you to go and interpret that in the unsigned form, so this would be 1 into 2 power 7, this would be 1 into 2 power 6 and so on. If I ask you to interpret this 8-bit value in the signed magnitude form, this one does not carry any weight, but this will start carrying weight from 2 power 6, 2 power 5, 2 power 4, 2 power 3 and so on. However, in 1's complement the weights are not attached to the positions. So 1's complement representation as well as 2's complement, which you will see later, are not positional representation techniques. So they have something which is partly position based and partly it is not. So we would not call it a position representation system. So in this case, if I want to go and take this number and interpret it as a decimal value, it is the same principle, right? It is starting with a 1, so it is a negative number, flip all the bits, so it will be 0000 followed by 1000. So 0000 1000 is 8, so that is equivalent to minus 8 then. So if we want to extend a number into more digits, more bits, then take the most significant bit and append as many bits as you want to the left. So that will be a valid 1's complement representation. So let us look at the number circle representation for 1's complement. So as before, I have the so I have 0000 0001 and so on, and it is in a number circle. So if I want to get the interpretation, this is number 0 and all the positive numbers are on the right side. If I go from 0, with 0, 1, 2, 3, 4, 5, 6 and 7. So at this point, if you notice, it is starting to become 1 as the first bit. So clearly these are not, so this side is not positive numbers, they are all supposed to be for negative numbers. Now let us see what these numbers are. This 1111 actually stands for minus 0, this one stands for minus 1, this for minus 2, minus 3, minus 4, 5, 6 and 7. So these are the numbers, these are the values if these 4 bits are interpreted as 1's complement. So it is all about interpretation. We have 4 bits, we want to interpret that in 1's complement, and that is how it works. So the way you can think about this is, if you go in the positive direction from 0, right, in this clockwise direction, it goes from 0, 1, 2, 3, 4, 5, 6, 7 and it stops at 7, because in this example n equals 4 and we cannot go beyond 2 power 4, we cannot represent 2 power 4 minus 1, which is 2 power 3 or 8. We cannot represent positive 8, we also cannot represent negative 8. And one thing you can notice is minus 0 and plus 0 are actually neighbors of each other in the representation. And if I go in the, so again even in this case, if I go in from here till here in the clockwise direction, the numbers are increasing. Similarly from minus 7, if I go in the clockwise direction, the numbers are increasing all the way to minus 0. This is still increasing, minus 7 to minus 6 means you are increasing minus 7 to minus 6. So from minus 7, if you go all the way to minus 0, it is still increasing. So there is a break here when we go from 1111 to 0000. Similarly there is a break when we go from 0111 to 1000. So even in this representation, if I draw a line here, all the numbers to the right side are positive and all the numbers to the left side are negative. And as in signed representation, we have negative 0 and positive 0 both. Right. So there is this interpretation called the 1's complement interpretation. Finally, let us look at this other representation called the 2's complement representation. In this, again the positive numbers are represented as it is, negative numbers are calculated by subtracting the magnitude of the negative number from 0 and we borrow from imaginary position. So as an example, what we do is, so there is a shortcut way of getting a 2's complement representation. You take the number, if it is a positive number you write it as it is, if the number is negative, so the first thing you do is complement, so you represent that number as though it is a positive number. If I want 5, right. So 5 is just 0 1 0 1, we represent as it is. If you want minus 5, we take 0 1 0 1, right, which is the positive 5, flip all the bits, that will give you 1 0 1 0 and add 1 to it, that will be 1 0 1 1. So that is the 2's complement representation of negative 5. So 1 0 1 1 in 2's complement interpretation would be minus 5. Here also positive integers are all 0, negative integers have MSB equal to 1. So positive integers have MSB equals 0. So the range, however, is an interesting thing. So there is a small change with respect to 1's complement. In terms of the positive numbers, you cannot represent more numbers than what 1's complement is capable of. So if I give you a n bit, if I tell you you have to represent something with n bits, then you cannot represent 2 power n minus 1. You can represent a number which is 1 less than 2 power n minus 1. However, in the negative numbers you can represent one more number. So that is why you have a less than or equal to here. So that means the range is asymmetric around 0, and it also means that the 0 does not have a two representations. So if I have n bits, I can represent 2 power n distinct values. The 2 power n distinct values in 2's complement are all the way from 0 to 2 power n minus 1 and all the way from minus 1 to 2 power n minus 1 inclusive. So in the positive direction it is 0 to 2 power n minus 1 minus 1, and in the negative direction it is minus 1 to minus 2 power n minus 1. So let us see some examples. We will take the same things that we did before. So 0 followed by 1 1 1 0. If I want to interpret that, if this is a 2's complement interpretation, then this is a positive number, 1 1 1 0 is 14, so that is 14 itself. If I want to interpret this 1 0 1 1, so I know it is a negative number. If I want the decimal equivalent of it, I first of all flip all the bits, so it is 0 1 0 0 and then I add 1 to it, right. So 0 1 0 0, I add 1 to it, it is 0 1 0 0 1, 0 1 0 0 1 is 9. However, since we started with the number MSB equal to 1, it is not 9, it is minus 9. Then let us look at 15, how to represent 15. So 15 is 1 1 1 1 in binary, that is only 4 bits. So I am asking it to be represented in 5 bits, all you have to do is put a prefix of 0. So 0 followed by 4 ones is plus 15. Plus 16 in the binary representation in unsigned form is 1 followed by 4 zeros. However, 1 followed by 4 zeros, if I represent that in 5 bits, then it is now going to be interpreted as a negative number. So 16 cannot be represented in 5 bits if there is a 2's complement interpretation, because we know that 2 power, so if it is 5 bits, so 2 power 5 minus 1 is 2 power 4 is 16, so x has to be less than 16. However, minus 16 is possible. So for minus 16 it is 1 followed by 4 zeros, right, that is 16, flip all the bits, right, that is 0 followed by 1 1 1 1, you add 1 to it, it is again 1 followed by 4 zeros, that is the representation for minus 16 in 5 bits. So for minus 16 it is actually, this looks like it is positive 16, right, 1 followed by 4 zeros is positive 16 in the unsigned interpretation, but it is minus 16 in the 2's complement interpretation. As before, you can take a number with a lesser number of digits and extend it to more digits. So 0 1 0 1 1, it is 5 digits. If I want to represent that as a 8-bit number, I can prefix zeros to it, 3 zeros. Similarly, if I want to extend a number, a negative number into more bits, I can add more ones to the front, right. So this is just like what we had for 1's complement interpretation. So going from a smaller number of bits to higher number of bits usually requires only sign extension. You take the most significant bit and copy it to all the positions which you have added. That is enough for 2's complement interpretation. The last, so now let us look at the number circle for 2's complement. For 2's complement, we start with 0 here and it goes as, so in fact there is no positive 0 or negative 0, it is only 1 0 here, then plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. So here also if I draw an imaginary line here, everything to the right of that is positive or 0, everything to the left of that is negative, and the negative numbers start here. It goes in this order: minus 1, minus 2, minus 3, 4, minus 5, minus 6, minus 7. However, this 1,000 is minus 8. So we will have 0 and minus 8 opposite each other. If it is a 5 digit representation, 0 and minus 16 will be opposite each other, and if it is a 6 digit, it will be 0 and minus 32 and so on. So this is the number circle for 2's complement. So I know that many textbooks do not carry the number circle, but this is a very useful way to remember how interpretations are done in 1's complement versus 2's complement and so on. So one thing I want to do is put the 1's complement and 2's complement side by side. So this is a picture for 1's complement and this is a picture for 2's complement. So let us start with just the positive halves first. You can see that, so let us see 0 to 7. So if I say 0 to 7, 0 to 7 has the same interpretation for all the positive numbers in both 1's complement and in 2's complement. So the representation does not change. However, if I take the negative numbers, right, so these are all the negative numbers in 2's complement, these are all the negative numbers in 1's complement. So if you see these numbers versus these numbers, so the right side one is 2's complement. If you see this, then there is 1 off. So where we have minus 0, we have minus 1, where we have minus 1, we have minus 2, where we have minus 2, we have minus 3 and so on. You can see that if the numbers are negative, then take 1's complement, and if you remove 1 from it, that gives you the 2's complement interpretation, right. So this is a trick to remember, and this is a common thing that that people do as a trick. So finally we will look at XSB representation or biased representation. In this representation, integer representations are biased by B. So a signed number x, if it has to be expressed using XSB, you add x to B, that is why it is called XSB. So B is XS, you add B to it, and if you do that, then the range of representation with n bits goes from minus B through 0 all the way up to 1 less than 2 power n minus B. Because you are representing with XSB, you cannot represent 2 power n minus B plus 1, you can represent only up to 2 power n minus B minus 1. So usually B itself is picked as 2 power n minus 1, we do not do XS5, XS6 and so on, we do XS3, XS7, XS15 and what not. Usually B is picked in such a way so that the complete range of bits can be interpreted. So if B is 2 power n minus 1, then we can represent all the way from minus 2 power n minus 1 to 2 power n minus 1 minus 1. So in terms of the interpretation, this is very similar to 2's complement, because it starts from minus 2 power n minus 1, it goes all the way up to 2 power n minus 1 minus 1. However, and 0 has only one representation. So both signed magnitude and 1's complement has two representations for 0, whereas XSB and 2's complement has only one representation for a 0. So I do not want to draw this in the number circle, but I believe this is something you can look at. So this is not a very hard thing. So I am going to show this in the number circle. So we know that in the number circle representation we can go from minus B less than or equal to x less than 2 power n minus B. So if I say that B is 7 or x is 7, then we should be able to go from minus 2 power 3. So B is represented using 3 bits, right. So we can go from minus 8, minus 7, 6, minus 5. So in this case x is 8 representation, I am sorry. So minus 5, minus 4, 3, 2, 1, this is 0, 1, 2, 3, 4, 5, 6, 7. So in this case B itself is picked as 2 power 3. So this is XS 8 interpretation. So this is a very useful thing. So this is the number circle for this interpretation. So what you will see is I will later upload a set of PDF files which has a very nice pictorial view of what are the different interpretations and where are they used and why. So, it is a nice set of pictures that is there at OCW's website. I will post that along with the slides for this one. So, let us look at some examples now. For a 5-bit representation and b equals 2 power 4, we have 10001. So, if I interpret that as 16 plus 1, which is 17. However, b is 2 power 4, so I have to subtract 16 from it. So, this is 17 minus 1, which is 16. Then 01100 is, if I interpret it directly, it is number 12, but its excess 16. So, 12 minus 16 is minus 4. So, this is the interpretation for minus 4. Then 0 followed by all zeros, right? It is already we have added 16 to it. So, I have to subtract 16 from it. So, it will be minus 16 and so on. And I suggest that you go and do the representations for 0 and 15 yourself. So, there are a few important points to remember. Given a bit vector b, which goes from bn minus 1 to b0, it can be interpreted in many ways. It is all up to the interpretation. So, given a n bit value, and if somebody asks you given a n bit vector, and if somebody asks you what is the value for this, the first question you should ask is, what is the interpretation that you have to follow? The interpretation will give you a value, but if you are going from one interpretation to the other, it may actually give different values. So, let us look at this bit vector 1111. If I tell you if I ask you what is the value for 1111, you should stop me and ask what is the interpretation you should use. So, 1111 in the unsigned representation is number 15. We have been using that all along, but the moment you use a signed interpretation, then this 1 is the sign and 111 is the magnitude. So, that is 7. So, this is negative 7. If you interpret the same thing using 2's complement, then it is minus 1. So, we should be very careful not to mix the interpretations. Mixing one interpretation with the other can be very disastrous. So, there is something else that you should remember. Arithmetic operations are basic for computers, and the number representation should be able to take two numbers in the same representation and produce results that are consistent in the same representation. So, if I have a circuit that is supposed to be adding numbers, you cannot ask for a number, you cannot ask for an adder which will take one signed number and another unsigned number and add them and so on. It does not make sense. Typically, you take two numbers which are interpreted in the same form, and the result that you should get when interpreted in the same form, the results should all be consistent. That is how we will design circuits. So, I will leave you with this table, interpretation of 4-bit binary numbers. This is something that is very handy. If you want to later go and do some arithmetic, I suggest that you go and keep this with you and work with this. So, this will come in quite handy later. So, I am just leaving it for completion's sake. So, this brings me to the end of lecture 1 for this week. So, in the next module, what we will look at is, we will look at how to do additions and subtractions in 1's complement and 2's complement representations. So, thank you, and I will see you in a little while. Bye bye.